So I was planning just to go through quickly that lecture, and so I can get it covered, because we have a quiz on that material due on Wednesday. So I postponed the quiz. Quizzes are usually due on Monday. This one, I pushed it to Wednesday. I pushed Lab 1 to be due on.
Not the 28th.
Sorry, not the 28th. You're right, the 8th. That should be the 8th. Yep, 8th. Yeah, so the quiz is due this Wednesday, the 8th, and then the lab is due on the 13th. I think originally it was due today. And I think, is there any issues? You guys okay with the lab? Okay. So, like I said, I'll just quickly go through first I want to go through quiz 2. So quiz 2 is last week's quiz, or the one that was due last week on Monday. First question, I think there was just a few questions on that one. What percentage of an SPI channel's master to slave bandwidth can be utilized when performing a series of single write transactions? So the 100%, right? Because you can keep the slave select high and then just keep issuing transactions. Now the problem here is that you still have to send the address and the data. So if you did that, you'd still have the address, but you would be using 100% of the bandwidth. In a daisy-chained SPI connection between master and end slaves, how many clock cycles are required to complete a full exchange? I actually didn't get to this 2 weeks ago, so I just gave everyone credit for this, and the answer is 8 times n cycles, but I'm going to talk about this today, go over this. This one is, what is the CPOL and CFA for the exchange below? This one's kind of tricky. In order to answer that, you have to look at when the data changes relative to the clock. If the data changes, if the first time the data changes in this exchange is the same time the clock changes, then it is a CFA is 1. So CFA, which is the phase, if that's 0, then that puts the data 1/2 clock cycle faster than the clock, ahead of the clock. Whereas if CFA is 1, the data and the clock change at the same time, and that's just something you just have to remember. And then CPOL is, that one's easy. You just look at what the clock is on its idle state. So before anything happens, the clock is 1, and so CPOL is 1. So CPOL and CFA are both 1. So again, for CFA, just check to see when the first, look for the first transition of the clock and compare it to the first transition of the data. If the data is ahead of is before the clock, then CFA is 0. If it changes at the same time the clock does, then CFA is 1. Okay, and then what data is written in the transaction below? Well, first of all, is this a write? Well, let's find out. We got to decode all the bits. So there's a header, which is so this is a transaction. An SPI transaction is at least 16 cycles. There's a header, which is 8 cycles, and then there's at least one data after that. So the header is the first half. And when I say first half, it's the first half of the transaction where the transaction is noted by the slave select being low. Okay, now you'll notice here that the way I've got this box drawn is actually a little bit after slave select goes low, and this is because of CFA is 1. So the data is basically delayed by the half cycle. So the way I drew this box was actually a half cycle after slave select goes low. But there's 8 bits in the header, and then there's 8 bits in the like the payload section. Now I assume, but the way the question's written, this is obviously a write. But so if we just make that assumption, and also we know it's a write too because only the MOSI is active in the payload part, right? So if this is a read, you'd have data coming from the slave back to the master, so MISO would be active. Now you could say, well, I mean, technically, maybe it is a read and the data coming back, it just happens to be all zeros. And for whatever reason, the master is toggling MOSI in that second byte when it doesn't need to. Because I mean, technically, that would be a don't care. MOSI would be a don't care on a read. But let's just assume it's a write. And so really all you have to do is just look at the bits in the payload section. And so the question here is, where do we look? Where do we read the bits? And this is the hardest part of SPI. Like, how do you figure out where each bit falls? Well, that's kind of tricky. I mean, obviously there's these dotted lines here that are kind of helping you. But you should look at this, CPUL and CFA. If they're both 1, then the data is going to be read starting on the second edge of the clock. So the rising edge, right? The first edge is falling, the second edge is rising. So if you look at the rising edge and you just count off 1, 2, 3, 4, 5, 6, 7, 8, and then once we get to the 9th one is right here, and that's where I've placed that 1 bit right on the rising edge of the clock. And so the 1 bit, I've put it right on MOSI. So in this case, MOSI is high, so it's 1, 1, 1, 0, 0, 1, 0, 1. So that data is going to be E5 in hex, right? So 1, 1, 1, 0 and 0, 1, 0, 1. So E5, that's the data being written. Okay, and then a bus protocol requires 3 wires named D in, D out, and clock. Is this a synchronous or asynchronous? Probably synchronous because there's a clock in there. I mean, I assume that CLK looks like clock, so probably synchronous. And then and this is a question on UART. What bit is missing in the diagram below? This one also, we didn't get to UART, so you should have got credit for this one. So this one is odd parity. Odd parity means there should be an odd number of 1 bits between the start and the stop bits. So we've got 0, 0, something, 0, 1, 0. I'm not including the last bit and the first bit because that's the start and the stop. So I'm counting just 1 bit. And so if it's an odd parity, then that means that missing bit must be 0, because if it was 1, then there would be an even number of 1 bit set. And I'll go over this again here. I'll go over this again. I'll review UART. Okay, and then for an SPI channel with CPUL 1 and CFA 0, when does the data signal change? So CFA 0 means that the data, remember, that means the data is in front of the clock. It's a little earlier than the clock, faster than the clock in that sense. So the data is going to change a half cycle before the clock even goes. Does that make sense? So do we have a timing diagram? Yeah. So in this case, CFA is 1, so the data and the clock change at the same time, right here. If the CFA were 0, the clock would come back by 1. So the data would come back by 1. So it would change before the clock. So what that means is that if CFA is 0, which it is in the question, right? Yeah, CFA is 0. The data is going to change on the opposite edge of the clock as compared to where it's read. And where is it read? Well, it's read on starting with the first edge of the clock, and if CPUL is 1, the first edge of the clock is going to be falling, right? So that means the data should be changing on the rising edge of the clock. Yeah, so the answer I have here is, makes the data change prior to the clock? Yes, it does. But after that, starting with the second bit, the data will change on the rising edge of the clock. Okay, so that's the quiz. Now let's go back into the let me check something here. Okay, so we talked about SPI. Let's see. Okay, so one of the issues with SPI is that you can only SPI is kind of set up for one slave. If you have more than one slave, it's a little dicey. There are 2 ways to do multi-slave, but they're not super great. one way to do it is to have the master with separate slave selects, one for each slave. The problem with this, though, is that you have to have multiple pins. You have to actually add pins to the master, one for each slave. And if you have like an Arduino and you've got I/O pins that you can use, but the Arduino hardcore, the hardwired SPI controller doesn't support this. So in order to get this to work on Arduino, I think you'd have to bit bang the SPI. You'd have to use the software to do all the SPI. But anyway, the other issue here is that you can have more than one slave select, and then the clock and the MOSI will just go out to all the slaves. The problem is MISO, because the slaves are driving MISO, and there's only one MISO input on the master. So all of these MISO connections coming from the slaves have to be shorted together. So this guy comes out and connects to the master there, but he's also shorted to this wire, which is this guy's MISO, and this guy's, so they're all kind of they all have MISO, they're driving MISO, they're setting MISO, but all these are shorted, and you can run into trouble when you have outputs that are shorted together, right? And I'll talk about that more in a minute. Option 2 is the daisy chain, where, and this is what the quiz question was asking, where you just run MISO out of the first slave into MOSI on the second slave, and the MISO on the second slave to the MOSI on the third, and the MISO on the third back to the MISO on the master. So you have MISO to MOSI, MISO to MOSI, MISO back to MISO. So what this does is create basically a big shift register where every time you do a transaction, you have to shift the bits all the way through all the slaves. And in order for that to work, whenever you do an exchange, remember the exchange was an 8-bit exchange on SPI. Well, now the number of bits you have to exchange has to involve all 3 of these slaves. So it's actually going to be 24 bits because you have to shift everything through everybody, right? So that's a solution. That's kind of similar to JTAG, which we'll talk about a little later here too. But neither one of these approaches is great. And with regard to the first one I mentioned, the separate slave select. Sorry, I gotta skip ahead here. The problem there, as I mentioned, is that you've got these slaves that are all, that's this blue-colored wire. They're all driving the same wire, and the problem with that is that MISO or the SPI uses what's called a push-pull driver circuit. And in order to understand how that works, you have to understand how these CMOS transistors work. You might already know this, but there's 2 types of transistors, an NMOS and a PMOS. And in digital logic, they're just treated like switches that are on or off. So you got 3 terminals here. There's actually 4 terminals, but one of them is implicit. It's not shown on the schematic. So there's a source and drain, which are essentially the same. You could think of them as the same thing, even though they're swapped on NMOS and PMOS. But the gate is the input. So the gate turns on or off the drain and source. In other words, it electrically connects them or not, right? And in the case of an NMOS, they're connected whenever the gate is 1, and in the case of a PMOS, they're connected whenever the gate is 0, and they're off in the other case. So that's why there's a little bubble here on the PMOS. That bubble just means there's an inversion there, right? So that's the transistors, and then normally a driver circuit like one on SPI is going to essentially just be an inverter. A CMOS inverter, but a big CMOS inverter. These transistors have to be made large to minimize the on resistance so they can drive a big capacitive load that would be an external wire, right? Because this external wire is going to be a lot of metal. It's going to have to charge up and discharge. So this is going to be like a driver is essentially a CMOS gate, or a push-pull driver, rather, is a big CMOS gate, but it's big, right? The problem is that if you have, like in the case of that multi-slave SPI, if you have 2 drivers, which I've called them endpoints, but these are just 2 chips basically, and they're both driving the same MISO line, so they're both connected to the same physical wire. The problem is that if one of them is trying to pull up, in other words, this guy is trying to put a logic 1 out, he is going to be turning on the PMOS transistor and turning off the NMOS. These are complementary. So either one's always on and the other one's always off. So I'd be pulling up turning on the top transistor, which is a PMOS, which is going to be shorting the output to VDD, right, to logic 1, and then the NMOS would be turning off, right? So basically, you're just creating a low impedance path between VDD and the output wire. That's basically what it's doing. But if you have another guy on there that's doing the opposite, so this guy is pulling down, he's turning on the NMOS and turning off the PMOS, you end up with a low impedance path from ground to the output wire. And what ends up happening is you end up sourcing current. So you get this rush of current that comes down from the power supply. It's going to come out of this chip, and it's going to go down through this pull down because you've got this low impedance path between power and ground. Between these two separate, they're two different chips, but you're creating this low impedance path, a short circuit, using these two drivers, right, that are in conflict with one another. And so that would be bad. So you'd end up with a lot of current. You'd also end up with if it's a 5-volt system, the output would be in between. It'd be like 2.5 volts or so, because you create a voltage divider that is roughly like having a resistor going up to VDD and a resistor going down to ground that are roughly the same resistance. So the output there would be about halfway, right? And so that would be an undetermined logic value, and you'd have a lot of current there. So to get around that, you can put these tri-state drivers in, which is basically a way to electrically disengage, right? And this is the way that MOSI thing would work typically, is that you would have a tri-state driver that would turn off and disconnect a slave from MISO who's not being communicated with because of its slave select. And you could do that, but now the problem is these things are really big now, because you've already got this big driver here, push-pull driver, with 2 transistors. And this transmission gate is another 2 transistors. It's basically just an NMOS and PMOS in parallel with another inverter, because when you turn this guy on, you want both transistors. See, in this case, only one transistor is on. But in a transmission gate, like a tri-state buffer, you want them both on or both off, so you have to add an inverter. So now you've got 2 transistors here, and another 4 transistors in the tri-state, and they're big. They're all big transistors too, because they're driving an off-chip load. So this is 6 transistors. It's pretty big. It's expensive. So a better way to do it is, well, a potentially better way is using an open drain style driver, which is it's just like half of a push-pull. It's just having the NMOS pull down, and then you have to add this pull-up resistor, which is about 10 kiloohms. And so what this does is, if the NMOS isn't pulling down, isn't trying to output a 0, then the natural default state of this wire is going to be logic 1. Now, you are going to sink some current through this resistor, and that will cause the voltage to drop slightly. But what you end up with is essentially a voltage divider, where on one side you've got 10 kiloohms, and on the other side you have, in this case, 2 1 megaohm, which are the off resistance of these guys, in parallel, which is 500 k ohms. So you'll get about a 10 millivolt drop here, right? So you're going to have a voltage drop. You'll never get it quite to all the way up, but it'll still be high enough that it'll be interpreted as a 1, right? And then if you want to output a 0, you just turn on, you just pull down, right? And the advantage here is that if you have a conflict, well, you won't have a conflict, because if this guy wants to put out a 1, he won't do anything. And if this guy wants to put out a 0, he'll pull down. But they'll know they're in conflict, because this guy will see, he'll see, wait a minute, I'm trying to put a 1 and I'm seeing a 0, right? So this guy will know to back off, that there's a conflict, right? And this, of course, assumes that you can read and write this wire. This wire turns into an input and an output in that case. I'm only showing the output part, the driver. But if they both try to pull down, well, that's okay too, because the amount of current you're going to sink is going to be limited by this 10 kilo ohm resistor, right? So it's not a big deal if you do put the bus in conflict. So as I mentioned, the leakage current here, if these guys are both off, meaning that they want to put a 1, these guys are outputting a 1, the leakage current here is like 10 microamps or so. It's on the order of microamps. And then if you turn one of these guys on, in other words, you want to put a logic 0 out, then you'll draw about half a milliamp down here. Now that's of course assuming that there's no load on this wire, which wouldn't be the case, because as I mentioned, this guy is going to have an input. But without a load on the wire, it's half a milliamp. So the point is that pull-up resistor limits the amount of current you get, and it simplifies the driver. Now we only require one transistor per output. You don't have to worry about the transmission gate, and you don't have to worry about the potential for there being a conflict, or at least a conflict that causes problems. If they're both on, then maybe 1 milliamp or so. Okay, so this is the technology that I2C uses. It uses open drain drivers. And so there's two wires. There's only two wires in an I2C link. There's SDA, which stands for serial data, and SCL, which is serial clock. So obviously it's a synchronous protocol because there's a clock. And you've got these, each one of these wires has to have a pull-up resistor somewhere. It's usually on the circuit board. Although the Arduino actually has the option where there's an internal pull-up resistor that you can enable optionally. But you got to have the pull-up resistor there somewhere. If you forget that, then it's not going to work. So that's a potential bug you can run into. But basically, the devices hang off of these two wires. And so, okay, so let me speed up. Okay, so I2C is also a multi-master bus. So any device on the bus can get mastership of it, and then it does a transaction where it sends an address out, and based on that address, another device who responds to that address will then be the slave in that transaction, but only for that transaction. So basically, in order to do a transaction, you go through this packet format, transaction format, where you put a start bit out, 7-bit address, and then a read or write bit flag, right? And then there's an acknowledgement that you get back from the slave. So the slave won't be defined until you get that address out there. But once the address goes out, then someone's going to answer, hopefully. And when they answer, they'll answer by sending an acknowledgement. Now you might say, wait a second, whoa. This is a half duplex bus. There's only one data line. How can I send an address out and then get an acknowledgement back? There's only one wire. There's no bidirectionality like there is with SPI. There's a bidirectional bus. Even UART has bidirectional. This is not bidirectional. So how is someone responding? How does the interrupt work if there's no bidirectionality? The way it works is that the slave actually takes over control of the data wire. So basically the data wire gets time division multiplexed in a way where after I put the address out, the slave gets control of it and then sends the acknowledgement. So basically I use the wire as an output for the address in the flag, and then I wait for someone else to drive an acknowledgement. And the acknowledgement is 0, which means that if no one acknowledges, remember the default state of that wire is going to be 1, right? So if no one's there to answer me, I'm not going to get an acknowledge. If someone's there, they have to physically pull down that SDA. It takes someone to actively do that. And so that's how the acknowledgement works. And then the data will either be sent by the master or the slave, depending on if it's a read or write, and then whoever is on the other side of that will acknowledge, right? Now, I believe you can do multiple of these before issuing the stop, but we won't worry about that in here. We're just going to consider one transaction at a time. That's why there's a ... here. Okay, so what is the start, and stop bit? Okay, so another problem here, or another difference between SPI is that SPI was an edge-sensitive clock. So I talked a lot about how when the data changes and when the clock changes and how the data has to be stable for a half clock cycle before the other edge of the clock, which is to sample the data, right? So you change the data on one edge of the clock and you sample it on the other edge of the clock, meaning everything is edge-based. With I2C, it's not edge-based, it's level-based. So the clock goes high and the data is sampled while the clock is high. So it's basically a latch instead of a flip-flop based system. So the data is not supposed to ever change when the clock is high. Because when the clock is high, that's like opening the door. The data comes in, and then when the clock goes down, it closes the door. But while the door is open, the expectation is that the data is going to be static, right? It's not going to change, right? So that makes it easier to read these guys too, because all you have to do is look at what the data is when the clock is high, and it's actually easier to read the bits than it is for SPI, where you have to look for the edges, right? So the waveforms are easier to read. Now the master side is the one that drives the clock. So even when the slave is sending data back, the master drives the clock, right? So the master always sets the clock, but the data is going back and forth depending on who wants to talk, right? So the clock is always driven by the master, data is whoever, right? Now the start and stop, this is a little confusing at first. The start is not really a bit, it's actually like a signal. And the way it works is that I mentioned that the data should never change when the clock is low. When the clock is high rather. When the clock is high, the data shouldn't be changing, right? Because the clock is high, the high level of the clock is the sampling of the data. And if you change the data when the clock is high, that'll confuse whoever's on the other side of the connection. However, when you do the start and stop, that's the one exception to that rule. So you'll notice that at the beginning, the clock is high, which it is by default when nothing's going on, because of the open drain, right? If you're not pulling the bus down, it's going to be high. And the data will be the same way. But the data gets pulled down first, and this is important, because the data, if the data changes when the clock is high, that's like significant, right? Because you're not supposed to do that when you're sending data. That means something special. So in this case, what that means is it's a start signal. So the start signal is defined as pulling the data low while the clock is still high, right? That is a signal that I'm starting. That's basically an arbitration signal. That means that I want to take mastership of the bus, so I'm going to do something unusual, which is to change the data when the clock is still high. Then, of course, after the data goes low, you also then drop the clock as well, right? Likewise, the stop bit works in a similar way, but in reverse. When you do the stop bit, you bring the clock up, and then you bring the data up, right? And again, data going from low to high when the clock is high is a special, not a bit, but a signal. That's the stop signal. That means I'm surrendering mastership of the bus. Now, after you get mastership, and there's mechanisms in there to detect if there's two devices that try to get mastership at the same time. There's a back off mechanism. I just assume that's there. I don't talk about how that works because I don't know how it works, frankly. But there's a circuit that will detect that. So once I get mastership of the bus, then I just send out the 7 address bits and the read or write bit. It goes from most significant to least significant. And I mentioned that after I send out those 8 bits in total, 7 address and 1 flag, then there's an acknowledge. So in this case, you'll see that there's an acknowledge after that read-write bit. The problem with the timing diagram here is that it's not obvious from the timing diagram who's setting these bits, right? You know just based on what slot they're in. So the first 7 slots, the first 7 bits are for the master, then the read or write flag is master, and then it's the slave is going to take control and do the acknowledge, right? But you can't tell that from the timing diagram. You just have to know based on the protocol. And then in the second 8 bits that are sent, which is the data, that'll either be the master or the slave, depending on if it's a read or write. But in either case, whoever it is going to yield control back to the other guy for the acknowledgement. So if I'm doing a write, I'm going to write out my data and the slave will acknowledge, right? Or if I'm doing a read, the slave will send the bits and I'll acknowledge the slave. So whoever sends data is always acknowledged by the other side. And so that acknowledgement is a way to know if there's a problem, which is something that SPI doesn't have. SPI, you'll do an exchange, you'll never know if your data went anywhere, right? Or if anyone was listening, right? But with I2C, you know. I2C is a more complex protocol, even though it has a simpler driver circuit than SPI. It's a more complex protocol. Okay, so that's...
Since the acknowledge is just 1 bit, is it just something worked or something didn't work is all it can really say?
Yeah, basically, yeah.
And I guess here 0 would be everything's normal.
Yeah,
Okay.
yeah. There's no other code words or anything. Yeah, Yeah, as far as I know anyway. Okay, so here's an example transaction. So to figure out what's going on here, it's actually a little easier because you know that, if you assume the start is good, right? And we could make sure though. So start is data goes low while clock is high, and then the clock subsequently goes low. So that's the start. Once you see that, then all you have to do is look at the bits, which are easier to find because now you can put the bits like right underneath where the clock is high. So now it's 1. You don't have to worry about edges anymore. Like SPI, you're looking for edges. Here, it's no edges. You just say clock is high, so I got 1, 1, 1, 1, 0. 1, 1, 1, 1, 0. That's 5, and then 6, 1, 1, and then that's 7. So the 8th one is the read or write. And then the 9th bit is the acknowledge. And then the next 8 bits are the data, and the 9th bit is acknowledge. So at a minimum, there's actually 18 total bits. And then also the start and stop, which are not bits. Start and stop are signals. But if you just look at the bits, there's 18 of them because there's 8 bits for the header plus the acknowledge, 8 bits for the data plus the acknowledge. So there's 18 clock pulses here in total. Okay, so there's the start, and then I put M and S to signify who's talking. So the address here is 7 bits. So 111 is 3, and then 1011 is going to be B in hex, or 11 in decimal. And then read or write bit, let's see, read is when the data is 1, write is when it's 0, because there's a little bar over the right, the W. So 0 means write, and what is it? It's a 0, so that's a write. And so then the slave says acknowledgement, which is 0, then the master puts the data out, which is 0011, which is 3, 00001, so 3, 1 is the data, and then the slave then acknowledges that with a 0. And then stop. So that's that's basically it. If this were, now keep in mind though that the number of times that the data line changes hands depends on if it's a read or write. So this is a write, which means I go from master controlling data to slave, back to master, then a slave. So it changes 3 times. Whereas if I'm doing a read transaction, the slave does the acknowledgement for the address, but then keeps going, keeps control. So there's only 2 changes of data control on a read, but 3 on a write. And that's just because if it's a write, you got to acknowledge and go back to the master to send the data once a write, right? If you're reading, then you acknowledge and then send the data. So the slave can hold on longer to control of the data line. Okay, so I got a question. What's the stop condition of I2C? Okay, so this question is actually easy because you know the answer has to be when SCL is 1, right? Because it's the whole idea is you're changing the data when the clock is 1. So just even looking at the last 3 words, you can tell that A is the right answer. But yeah, it's the rising edge of SDA when SCL is 1. Okay, I mentioned that. Okay, let me back up here and talk about UART. UART is the another protocol. I'm sure you've heard of UART. UART's used for just like consoles. UART uses a push-pull driver design like SPI, but it's not master-slave. It's just a bidirectional. It's just 2 bits going in either direction. So you've got a transmit on one side is just connected to the receive on the other, and the receive on one side is connected to the transmit on the other. So you have to cross the lines, right? So if you have a TX and an RX pin on 2 devices, to get them to communicate, you have to use a null modem adapter. You have to cross them. The TX goes to RX, RX goes to TX. So now you don't have to do that with SPI because you've got master and slaves and the different pins for different things. Because this is just a bidirectional, you have to cross these wires. And then for whatever reason, the ground is shown here, but this is kind of superfluous because SPI and I2C also, of course, assume that there's a common ground. These are electrically consistent peers on all of these channels. So I don't even know that it's shown typically. I think that's why I put it in there, but you would always have a ground shared on all these guys.
So does the R and the T mean there's no master and slave, and that's why they're proxies?
Right, exactly. Yeah, it's just a conversation between two entities. And you don't even need them both. You can have a single direction. You can just eliminate one of these wires and just have data go one way. Usually it's both ways though. Okay, so UART UART doesn't have a clock though. That's the other difference, right? There's no clock. So the clock is generated internally on each side, and it's generated by setting a baud rate. So you give a baud rate, you have to determine that ahead of time. The baud rate is generating an internal clock that's used for driving and sampling the bits, right? The problem is that I mentioned that if you change a bit when you're sampling it, like if the driver changes it and it's in a state of change, right? It's changing, and the other side is sampling it on the clock edge at the same time. That's going to cause the receiver to go into metastability. So the receiver is going to get an error, right? It's not going to read that correctly. And so how does UART address that? Well, it does it by using a really slow clock, which reduces the likelihood of that happening. So the clock rate in I2C and SPI is megabits per second. This is kilobits per second, right? But it also has a parity bit, which I talked to when I was going through the quiz. There's a parity bit that detects errors, and it's also used for that purpose as well. This is error checking mechanism, error detection mechanism. The parity bit, however, is optional, although so you don't always have it. The other thing with UART is the bits come in least significant to most significant, so they come in backwards order. Unlike SPI and I2C, it's usually most significant to least significant. Although with SPI you can do it the other way. With I2C you can't, because that's part of the I2C standard. Okay, so there's a start bit and a stop bit. So the start bit is the idle state of the bus is 1, logic 1. I don't know why they do that. This is a push-pull system. It's push-pull, so they didn't have to make the idle state 1, but they did. That was a decision. But the start bit is then when there's 1 bit period that's 0. And then likewise, the stop bit is 1 bit period where it's 1. So the reason for that is that if your start bit is a 0 and your stop bit is a 1, that guarantees that you're going to have at least, well, I shouldn't say at least, because it's not like there's a clock. This is the data line. So what this means is that there's going to be actually exactly 1 falling edge of the data in between each 2 consecutive values you send across this thing, right? Because the stop bit is 1, the start bit is 0. So going from the stop bit to the next start bit, you're going to have this falling edge. And this is what it's keying off of. It's looking for a falling edge. If it thinks the bus is idle and it sees a falling edge, it's like, okay, there's something coming across here. That's my start condition. So it looks for this falling edge. And then the start bit has to be asserted for 1 bit time. And there's no clock, so what's a bit time? It's whatever the internal clock says it is, right? And then you just send the bits over serially, and then you give the stop bit. And that's essentially the format. Usually it's 8 bits, but you can have 7 bits or 9 bits. That's configurable. But either way, you have to agree on that ahead of time. The two, if there's not an agreement, you'll get corrupted data. Usually when I do this, I just use trial and error, frankly. I try different settings till something works. Because sometimes it's hard to find what the settings are supposed to be. Okay, so, I mentioned why is the stop bit 1? Is so you can have at least 1 falling edge in between consecutive bytes. There's also a parity. This is optional. A parity is a bit that comes right before the stop bit at the end that forces the number of 1 bits between the data and the parity to be either even or odd. So if you have even parity, this part's a little confusing. If you have even parity and there is an odd number of 1 bits in the data, then the parity bit is 1. You might say, no, it shouldn't be 1. It's indicating whether there's an even number of 1 bits. No, it's actually the opposite. What's happening is that the parity bit is being used to force the number of 1 bits to be even or odd, which means that the logic is kind of reversed. If there's an even number, if you're even parity and you have an odd number of 1 bits, then the even parity bit is 1, which will force in total the number of 1 bits to be even, right? Yes?
I'm a little confused. What
Okay, so a parity error then, when you have the parity bit, you have the potential of a parity error. And that's when the receiver counts the number of 1 bits, and it's not what's expected, right? So if you have even parity, you expect the number of 1 bits to be even. But if the receiver sees that's not the case, then it knows, oh, there must be an error. There's a that error could be caused by noise, or it could be caused, most likely it's caused from synchronization. It's because there's no, it's because of metastability. It's because there's no clock, right? That's usually what the errors are caused by. Because there's no clock, so these guys have to have an internal clock, which is fine. I mean, the internal clock will give the same clock speed, right? Which means the bit periods are the same on the sender and the receiver, right? But the phases are not locked in. That's the problem, is the clock phase. The clock phases are not, there's nothing to make the clock phases consistent. So even though the clock periods are the same, because the phases are different, you could end up reading this guy when he's in a state of flux, right? You're changing the bit. If I read, so you don't know when you're reading these bits. You know how frequently to read them because of the clock period, but you don't know when to read them exactly within that period. So if you happen to read, if this guy reads on that edge, then you're going to get an error. And there's just nothing you can do to avoid that. It's just random chance. Just depends on how your clocks are aligned when you generate them. Okay, so so this is 7 data bits, no parity, 2 stop bits. You can't have 2 stop bits, and all that does is it extends the amount of time between 2 consecutive bytes. But usually there's 1 stop bit in practice, at least in my experience. But make sure you don't count the stop bits when you're doing your parity. They're not included in that. Okay, so that's UART. Any questions about? I went through that kind of fast because I kind of got behind with the last week. But if you have any questions, let me know. Okay, so we covered I2C, UART. Okay, the last protocol here is JTAG. This one is kind of interesting. This JTAG is used for debugging circuits, and it's another serial protocol, and it's kind of similar to SPI, but not exactly the same. It's got this one unique characteristic. It's the way that you control it. So it's got a TDI, test data in, which is basically MOSI. It's just the input into the slave. TDO is the output from the slave, so that's MISO. So this is like MOSI and MISO. Then there's a clock, so it's synchronous. And then you have, instead of slave select, you have this thing called TMS, test mode select. And this thing is radically different from the slave select. Slave select is just low or high depending on if you're talking or not. This thing is actually a single bit signal that allows you to control the devices, all the slaves on the JTAG chain. Now the chain is actually formed from daisy chaining the TDIs and TDOs, which again is like SPI, how I showed you the daisy chained SPI. But with JTAG, it's designed more specifically for doing that kind of chaining. And then there's a test reset, which is an optional pin. I think in my experience, JTAG's usually just these 4 pins. So there's 4 signals in the channel. And so you have these devices, and the TMS and the clock are fanned out. So they all just share the same, they're all just seeing the same global clock and TMS. The TDI, though, is a shift register. So TDI comes out of the master, goes through the first slave, goes out of there into the next slave, and then goes you have this chain where you can send data all the way through. Okay, but the main difference, though, between SPI and JTAG is the way that you control these guys. You do it through this TMS. So all of the devices on the JTAG chain have this thing called a test access port controller. So this is basically, the idea is that you have a chip. Most chips have a tap somewhere on them, if not multiple taps. So you have like a GPU, for example, or a CPU, or any kind of chipset you have in your computer will have this tap on it. Phones have this as a way that if you go into the Android SDK and you plug your phone in and you talk to it through the Android debug ADB, that's using JTAG, right? JTAG over USB, but still it's a JTAG type process. And so And the FPGAs we use in class also use JTAG as well. But again, they do JTAG. You can put JTAG on top of USB as opposed to just running the 4 wires. So the TMS is actually controlling a state machine on each of those taps. And so by putting a sequence of bits in the TMS, you can get all of the taps to go into one of 16 states, depending on the sequence of bits you put out. Now the TMS is clocked just like the data, so they both use the same clock. But you put multiple bits out in consecutive clock cycles, and you can actually traverse this state machine. So you start out in test logic reset. If I put a 1 out and clock it, I just stay there, right? And as long as I'm putting 1s out on the TMS, I'll just stay put. But if I put a 0, I'll switch to this run test idle. Then if I keep putting 0s out, I'll stay in that state. But then if I put a 1 out, I'll go to this select data register scan. If I put another 1 out, I'll come out to select instruction register scan. Or if I put a 0 instead of a 1, I'll come down here, right? So every one of these states has 2 outgoing transitions that correspond to the TMS bit that you see in that cycle, right? Now in some cases there's a wraparound that allow you to stick around in the same state for a while. There's other states like capture DR that you can only be in there for 1 cycle, because once you get in there, it doesn't matter if you see a 0 or a 1 on the TMS, you're leaving that state. You're leaving that state no matter what, right? Because there's no wraparound, there's no loop back transitions there. So the way that JTAG works is there's an instruction register and a data register. The instruction register is the address. It's like the SPI address. And so you run the state machine to get to this shift IR state, and then you stay in there, and while you're in there, you start shifting data in through the TDI, and that allows you to shift bits into the instruction register. When you're done with that, you leave that state and you go to update IR, and that registers the instruction register. They call it an instruction, but it's really an address. And then, once you've got that, you can then go to do the same thing, but now you can go to the shift data register, and you can start sending data into that address, right? And that's basically it. So it's really doing the same thing that SPI is doing, really. The only difference is that SPI, you send the address in as part of the transaction format, whereas here you have to go through this rather elaborate process to shift serially the address in one state, and then go to another state where you send the data in, right? Now, why do they do it that way? I don't know. I mean, I know that there's other functionality in each of these states, but the shift DR and shift IR are the main two states. But there's other stuff that happens in these other states that's more obscure. But the point is that the way that you get addresses and data into this thing through this TMS.
Devices that use JTAG have, I guess they could have less states by just not using them or having the device not do anything. But
yeah,
are they the same across?
Yeah, it's part of the standard. So they're all supposed to support those 16 states. It's supposed to be standardized. Yeah, because you can get a generic JTAG master and plug any device into it and probe it. Yep. You know, you can actually do a scan, and you can scan all the registers and figure out which devices are connected. And in fact, I'm going to show you on the, well, I think you've taken 611, so you know that when you plug the FPGA in and you go in the programmer and you connect it to the board, it already knows what FPGA is on there. And it does that by reading there's a special instruction that identifies the device. Yep. So it reads that identification code out, and then it looks in a table and it says, oh, that's the Cyclone 4E FPGA, and it knows that. And it can get all that just by reading the JTAG. You don't have to tell it. It can glean all that from the JTAG transactions. Okay, let's see. So one of the neat things about this state machine is that if you put 5 or more 1s in, you'll always go back to the test logic reset, no matter where you're coming from. So that's a good way to reset the system, even if you don't know what state it's in. Okay, so let's.
JTAG is also daisy chain. So
yes.
Like a single PCB with multiple JTAG.
That's the idea.
You have to go through them all.
Yeah, that's the idea. The idea is to have minimal number of bits, because this is just test logic. So designers don't want to spend a lot of real estate. They don't want to have a lot of circuit board resources. The idea is it's like a side channel. It's something that's very low cost, but it can give you access to a lot of stuff on a circuit board. It's slow, but it gives you really good coverage. You can basically read out the internal state of every chip on a circuit board just from this one JTAG chain that wraps around, and it's just 4 wires. So that's the idea, is that it was meant to be as cheap as possible, but yet capable of debug. So like I mentioned, this is just another way to look at it. There's you could think of it as by setting different instructions, you could think of that as a mux. So each of those instructions corresponds to a different register. So there's an ID register, which I mentioned, that identifies the thing. Bypass register, there's just sends data through if you don't want to actually involve somebody. Boundary scan. Now, by the way, all of the devices on the chain are going to be in the same state, but you don't have to put the same register in, the instruction in. They're all, so you have to configure the whole chain to say read the instruction register, but then when I shift the bits in from TDI, I can make it so they all have different. I can set up one to be bypass, and I can set up another device to do ID register, right? I can select specific data for each of those. They're all in the same state, so they're all they're all bringing in an instruction register. You can't have them, because remember, the TMS fans out to everybody, connects to everyone. So they're all in the same state at the same time, but the data that goes into the registers can be different. And I think that, by the way, is the reason. That's probably, now that I think about it, I never even thought about that, but that's probably why they don't use SPI for this, because SPI, it would be harder to have the daisy, well, could you? No, because even with the daisy chain, yeah, it would be tough to work it out with the daisy chain and SPI where you could put a different address in each device on the daisy chain. I guess you probably could do it somehow. But anyway, this is designed to be able to isolate specific devices on the chain, even though they all have the same TMS input.
It seems like SPI was never designed to have multiple devices.
Yeah, exactly. Okay, so so that's the idea, and you could think of it like the instruction decoder is what sets these mucks. So you go into the instruction decode, or the instruction read, what is it called? You put them in this shift IR state, and you cycle bits through. And so you're cycling bits through, and every one of them is going to get a different instruction, which is then going to set these muxes. And the reason why you have a mux and a demux here is because, or demux and a mux, is because the TDI, like once you select one of these, like once you select, like say the boundary scan, bits coming in TDI are going to be routed through the boundary scan register and then back out, right? So that's the reason why they show it like that, So you've got a combination of muxing and the shift register in there. Okay, and then there is other buses that I haven't mentioned, and I'll just mention them briefly here. There's something called a controller area network, which is used for automotive applications. This is like in your car. It's used quite a bit for reading any kind of controller-based system, but it's very similar to I2C. It's a variation on I2C. You might also see I2S, which is for digital audio, and it's also a variation on I2C. There's a couple differences. In I2S, there's a word select pin that's used to detect to specify the right or left channel for which speaker you're sending the audio to. Okay, and we have a comparison, and that's it. Okay, so then we can move on to the next lecture. So in the next lecture, my intention was to show a tutorial for the FPGAs that we're going to use in the next lab. So I think I mentioned this at the beginning, but in this class, when we first developed this class, we were using Arduinos, and then later we ended up switching to the FPGA board so we can have a consistent platform for 317, 313, and 611. The Arduinos are kind of flimsy, they're tiny, and the thing I don't like about them is that they have very limited debugging capability. you can't do line by line step debugging on them. I mean, well, technically you can, but the ones we had couldn't do it. It turns out, just so you know, in case any of you guys use an Arduino, the Arduino has a reset pin on it. And on a typical Arduino, and when I say Arduino chip, I'm talking about the classic Arduino chip, which is the Atmel 328P. There's other Arduino chips, but that's the kind of the de facto one, the original one. There's a reset pin. And on the Arduino board, that reset pin has a capacitor to ground, which is typical for reset. So you hit the reset button, it charges the capacitor, and it basically sends a reset signal to the device, and then the capacitor discharges. So it gives it a few Mississippis to be in that reset while the capacitor discharges, basically. But there's a secret feature where the reset pin, if you don't have a capacitor to ground, you can send a special protocol into that thing, which gives you access to debugging the chip. It gives you full debug access, where you can actually use a step, you could do a full debug. In order to do that, though, in addition to not having that capacitor there, you also have to have a debug module, a special debugger, which we have, actually. We bought them for this class, but we bought them for flashing the firmware, not for the debug. The board had the soldered capacitor, and there's no way to take that. We never figured out a way to take that capacitor off, so there was no way to actually use the debugger. So with the FPGA boards, we have full debug support, so that's why I decided to switch. And also, it also gave us the opportunity, I don't know if you guys know this, you know from 611 we designed the CPU, and then in 313 we used their CPU, but we're able to build a much more complex system on chip. But we never combined the two. We never use System Verilog to add components into the 313 software.
A little bit of that, if you actually take the time to understand, you're building the CPU and you're connecting the hex displays and the switches to it, but I mean, that's just one peripheral. Yeah,
but you're not designing the Verilog for those, right? You're just using off the shelf. So in this class, I thought it was a good opportunity to actually do that, to finally do that. Now, you don't have to take any courses, though. You don't have to have taken 313 or 611. I don't think you guys have had, right? You guys haven't?
I've taken 611.
Oh, you've had 611? Okay, have you?
Both of those.
Okay, oh, great. Okay, well, then this will be easy for you then. So anyway, we're gonna use the same boards, but it also, the other thing too is I also wanted to spend more time with the hardware debugging, something we didn't do much of in 611. We did simulation and model sim, but we never used signal tap to actually use logic analyzer on the boards. So we'll do that in this class as well.
Is it 611?
Yeah. Yeah, 611 is design a CPU from scratch in System Verilog and put it on this FPGA board. So you kind of just build your whole FPGA, I mean your old CPU on the FPGA. In 313, the idea is that you use the same FPGA, but you take IP, intellectual property. You take a bunch of blocks and you drop them in there, and you kind of, like Legos, you kind of build up a complex system that has a bunch of components. It could even be in 313 we end up doing a multi-core, 4 processor cores, and a little VGA controller and all this stuff is all on that FPGA. But you never actually design the hardware. You never actually get inside there. It's all it's very abstract. You just drop the things in, and you don't really see the way they interact with one another on the board. So in this class, the idea is that we're going to now finally be able to develop our own IP and put it inside there. But it's going to be a real simple IP, because I don't want to, we're not going to have time to cover a full System Verilog in here like we do in 611. So, you guys, so I guess 2 of you guys have seen all this already.
I had a question about the Arduinos. When you're talking about the the reset pin, is that actually sending a signal to the in order to debug the code using the reset pin? Is that actually sending a signal to the processor, and it's like a hidden instruction or just a public instruction?
It's a protocol that is specific to Atmel.
Okay.
And it's kind of like that TMS thing that JTAG uses. It's a specific bit pattern that makes it do different things.
Okay.
But so if you just put a 0 or 1, it just acts like a reset. But if you put a high-speed pulse, like a bit stream in there, if you have the protocol, if you know the protocol, which I don't even know if I don't even think it's an open protocol. That's why you have to buy their debugger. But if you send a specific bit pattern in, it unlocks the ability to get your hands inside that chip, and you can. It's like basically like it's JTAG essentially.
Yeah, rather than just like emptying whatever's in the registers, with the reset, it would let you kind of go into probably a state machine.
Yeah, well, it lets you freeze the CPU, which is the big thing for debugging. You want to be able to freeze it.
And see the state.
Like if you're running a CPU in a debugger, you hit like on these boards, you hit the pause button and it just freezes, and then you go in, you can see the state, right? Or you could set a breakpoint. You could say freeze on line 12, and once it hits line 12, it just freezes. It hits a breakpoint, and you can go in and you can inspect the state. You could look at registers, you could look at the memory. And you can do that with the Atmel chip, but only through that reset pin, and it's almost like a secret capability. But if they have the board, if the board doesn't allow it, because they soldered that capacitor on that pin, with the capacitor there, the capacitor will not allow you to.
You can't get the rate through.
Yeah, because it acts as a low pass filter. The capacitor will low pass filter that thing. So even if you try to send the bit stream in, the capacitor will take all the edges out of it, and you won't.
And you guys never found where that capacitor was?
No.
Yeah, who knows?
No.
Who knows which one it is?
It's possible we could have modified the boards, but we never got to that point, and so that was the problem with those. But the other issue too is that like even to get a console on those, like to say hello world, we had to like basically do it through a pretty flimsy connector and use Minicom, and it was a hassle. With these boards, it's just much easier. You plug in that USB blaster and you get like complete control over everything.
That's what FPGAs are for.
And plus, the other thing in this class is we want to focus on control theory. And a lot of controllers are implemented on FPGAs because they're deterministic. You know exactly what they're going to do in every cycle. Whereas with a CPU, there's uncertainty introduced with the cache and the page table and interrupts and other things going on. It's hard to know. It's hard to get real-time constraints. Okay, no, it's no problem. Let's see, we go to 335, right? Okay, so. So I'll just run through these real quickly because you guys have seen this already. FPGAs are the blank slate. You program them and they implement whatever logic that you design for them. So they're a programmable logic device that when you turn them on, they're just a paperweight. But after you program them, they will behave like an arbitrary digital logic circuit as long as it fits on there. And we're using the TerraSIC DE2. And we're using Quartus 2, which is the main IDE. And Platform Designer, which is another IDE that allows you to use the IP blocks and assemble the system. And then the command line tools for programming. Did you guys use Eclipse for the software?
Yeah.
Okay, so
313, they're still using Eclipse.
So we stopped using Eclipse because it's flaky.
It is.
Half the time you tell it to run and it doesn't run and you don't know why. So we quit using it. Well, I stopped using it. I think Rasha's still using it. Okay. Because that's what she used when she TA'd the class with me. Charles and Philip and I developed the command line tools, which I think are a little better.
I've seen that when you showed I went and looked at some of your shell files and was like, wow, this is really nice. It's headless, so everything's fast.
Yeah, I like it better. Plus, you can use the GDB debugger and make files. Like you don't have make files in Eclipse. They're a proprietary make file system or build system. So so Platform Designer is basically the hardware design, and then we'll be writing software on it as well through the command line tools. So to launch Quartus, you get the Quartus window, and then the next part of this is just kind of a tutorial. I believe this is the same one that we do in 313. So you create a new project, and you have to set up the device. And I'll give a demo of this next lecture. You import assignments. So you import the pin assignments. We'll give that file is available on Dropbox. And then you have to add a system Verilog file. We just call it lights as an example because it's one of the blinking lights things tutorial. And then you open Platform Designer and you start adding a bunch of modules to it. So we add a processor, and we're using this is a Neos 2 processor, it's a MIPS processor. And then we add an SD-RAM interface, clock manager. The clock manager takes the 50 megahertz clock that comes from a crystal, and it'll use that as a reference clock to generate an actual internal clock. In our case, we're actually still generating a 50 megahertz clock. So you might say, what's the point then? Because the clock manager reduces the jitter. The crystal has more jitter than you get with the phase lock loop. So the clock manager basically cleans up the clock that comes from off chip. And then we add some different clocks for the SD RAM. And then we add a UART, which gives us, this is the JTAG UART. Now this is kind of interesting because we talked about UART, and we talked about JTAG, and actually this doesn't even use that, it uses USB. So this thing is a UART that runs on top of JTAG, which then runs on top of USB, somehow. But in the end, what you get is a console on your workstation. So when you print something on the code that you program this thing with, it'll print it on the console. But it's like I said, it's a kind of a convoluted. Now with the Arduino, on the other hand, we actually had UART. There was 2 physical wires that we would run into. Well, actually, though, we still went over USB though at some point. We had to go UART to USB. I think we had. I don't remember how we did that now. We had an adapter. And then you end up with a platform design that looks like this. So this is a bit confusing, but basically it's an Excel spreadsheet of all the components you want to add. And so the components are in bold. So these are the actual components. The stuff underneath of them are the inputs and outputs, which then you can connect to other modules through this column. Now this is a horrible way to do it. The other way to do it would be to have like a block diagram, and that's the way Xilinx does it. But even that can get really messy because you can end up with blocks all over the place and big rat's nest of wire. So no matter how you do it, it's tricky.
And now that I know that in the end this is just going to generate Verilog for each of these blocks, I'm like, I wish I could just write the beginning lines.
Yeah. Except the reason that's not practical though is that if you look at some of these are wires. So clock is a wire, reset's a wire, but this data master is not. This data master is an Avalon master. And this is actually comprised of multiple signals. Now, luckily, Avalon's actually not that complex. It's pretty simple. We'll actually be building an Avalon peripheral in this class. But it's still multiple signals. So this one wire is kind of like having an SPI channel, essentially, where it's one channel but multiple sub-wires in there. Except with Avalon, it's a parallel bus too. It's not a serial. So usually these on-chip buses are parallel, meaning it's 32 bits every cycle or 64 bits every cycle, as opposed to 1 bit. Okay, so yeah, we've got a bunch of stuff, and then you have to make these connections manually, and I'll show you how to do that. And then you generate HDL, and that's when it generates the Verilog HDL that you actually program onto the FPGA. Okay, so let's see, how much time do I have? So I'm just about out of time, so I'll go ahead and I'll just stop there.